All right, Unit 1, Lesson B, Classification of Matter. Today's lesson is basically going to be going through the vocab of matter. So, what do we call different kinds of matter? Do you remember in biology having dichotomous keys where the key would have two choices and it was either a yes or a no? And you worked your way through until it identified what the item was? You had to do it for your 8th grade science assessment, and you used it in biology. This is kind of a dichotomous key for matter. So matter up here is our biggest group, matter, anything that has mass and takes up space. So we talked about this already, has mass, takes up space. So that's pretty much anything that you're going to come in contact with here on Earth. So all of that stuff. Well, it's a really big category. So we're going to break it down into smaller groups. Is it uniform throughout? So what they mean is if you take two samples, if you grab two random samples of the substance, does it have the same composition all the way through, or will it be different from one piece to the next? Granite they like to use for an example a lot because they think you remember it from earth science. Granite, that rock that has all of the pretty little speckles in it. If I take a big chunk of granite and I cut it into pieces, and I look at any two pieces with a magnifying glass, you're not going to have the same number of black speckles and gold speckles and red. It's going to vary from piece to piece, so it's not exactly uniform throughout. Being different throughout is called heterogeneous. So this prefix hetero means different or uneven. So they'll talk about something being a heterogeneous substance if it is different throughout or if it's unevenly mixed. So examples that the state likes to use, granite I already talked about. They like to use soil as an example. Now when you grab a handful of soil, there's little pieces of rock, there's sand, there's some decayed organic matter, you might have some chewed up leaves, you might even find an earthworm in there. Heterogeneous. It's not the same throughout, it's different. Uniform throughout is going to be the homogeneous mixture, and this prefix, homo, means the same, or when we're talking about substance, even. It's going to be evenly mixed. So if you take a substance and you grab any two pieces of it, and it's the same stuff. So if you've got a container of vanilla ice cream, you take a scoop of vanilla and you put it in a bowl, you take a second scoop of vanilla, you put it in a second bowl. They should both taste the same, they both have the same composition, they have the same stuff in it. If you have a jug of distilled water, when you fill up your wash bottles from my distilled water, every time you get water out of that jug, it should be the same water. H2O, it's going to have the same composition, same formula. So that's homogeneous. Think of heterogeneous and homogeneous as adjectives and not necessarily a category. So they're adjectives. Okay, heterogeneous, it's unevenly mixed. Mixture is what we're going to call the stuff itself. Okay, so if it's heterogeneous, that's an adjective. It describes it. We're going to say it's a mixture. Two or more things physically combined. Two or more things physically combined. And if you look down there, this little chart counts milk as a heterogeneous mixture, and milk in its raw form is going to separate out into the cream and the whey. And, you know, they take the cream off and make things like whipping cream or cheese from it. The stuff that you get in a little carton, if you look really close, it's going to say it is homogenized milk. In a homogenized milk, they've blended that fat throughout and broken it down into little tiny pieces. So if you were to take a dropper full of it and put it on a slide and look under the microscope, you would see different sized fat globules floating around in the whey. So that's why milk is over here at heterogeneous, because the size of those fat globules, if you look really down at a microscopic level, it's different. And if you take raw milk, it's going to separate out. So whole raw milk, heterogeneous. The stuff you buy in a carton, for our purposes without a microscope, looks homogeneous, and that's because it's been homogenized. Now, homogeneous, again, is an adjective for evenly mixed, and homogeneous is going to come in two big categories. It's either going to be a pure substance, meaning it's made of one type of thing. Pure substances are made of one type of thing. Or it's going to be a mixture, and a mixture is made of two or more types. Yeah, pretend that's an R. Two or more types of things. So when you decide that a piece of matter is homogeneous, it looks the same throughout, you have to figure out, can I separate it by physical means? So if you can separate it by evaporating a part, by filtering it, by boiling it and recondensing part of it, any of those types of physical means, then it's a mixture. It's made of two or more things, and a homogeneous mixture is called a solution. This is really important. Homogeneous mixture is a solution. A homogeneous mixture is a solution. Memorize that. They'll ask you which of the following is a homogeneous mixture, and what they're really asking you for is which one is a solution. Homogeneous mixture, solution. I've said it a whole bunch of times now. Memorize it. Homogeneous mixture, solution. The trick here is that when something's a solution in chemistry, it's usually made with water. And when it's made with water, we put a little AQ after it. So if you see something with an AQ, you're going to read that as dissolved in water. AQ, aqueous, dissolved in water. So when you see NaCl, AQ, that means sodium chloride dissolved in water. So an aqueous solution of sodium chloride, that is a homogeneous mixture. Or salt water. Salt water, probably the most common example that they use. There's lots of things that can be solutions. Air is one gas dissolved in another gas. So in that case, nitrogen makes up the background and all the other gases are dissolved in the nitrogen. So air is a solution. Steel is a solution. Most of steel is iron, but a piece of steel isn't pure iron. They have other metals dissolved in there. Even though it's a solid, that's still considered a solution because steel looks the same throughout, but it's really two or more metals in there, and if you melt it back down, you can actually separate the pieces back out. Now, a substance has only one type of thing in it, and there's going to be two big categories for substances. So substance, only one type of thing in it. The only way that you could break it down would be chemically, and even then sometimes you can't. So that's going to be our question here. Can we chemically break it apart? If the answer is yes, then it's a compound. Two or more atoms chemically combined. The trick for picking out a compound is look for the capital letters. So in the previous unit we said that when you write elements, the first letter has to be a capital letter, the rest are lowercase. So if I look at a formula and I see 1, 2 capital letters, it's a compound. Water, H2O, 1, 2 capital letters, compound. Okay? If there's only one capital letter, one capital, then it's going to be an element. So even if you see a subscript, when they write oxygen, they're going to write O2, one capital letter. This one is an element. So an element can't be broken down at all, neither physically nor chemically. It's made of only one type of atom, one capital letter when you write its formula. It is the simplest type of substance. These are the things that are on the periodic table. Compounds, two or more elements, chemically bonded together. You're looking for two or more capital letters. So let's just look at the vocab really quick. They're listed out for you. These are the way you'll see the definitions written. Um, Typically, it's the way that the state's going to say them. A substances is something that contains one type of matter in it. Substances are going to be either elements or compounds. Elements, a substance made of one type of atom. Compound, two or more elements chemically combined. That's the way that you typically see it written out on questions on your final. Heterogeneous mixture, two or more substances unevenly distributed. Homogeneous solution is two or more substances evenly distributed. Keep in mind that a substance is considered homogeneous. Homogeneous and heterogeneous are adjectives. A homogeneous mixture is a solution. Solutions with water are called aqueous. We use the AQ. So if we look at some pictures of things, if I had a big vat of candy, I'd go to one of those stores, unevenly mixed. There's definitely a bunch of different substances in here. This would be a heterogeneous mixture. So this one's heterogeneous. Over here, there's water, there's milk, there's honey, there's this brass key. They all look the same throughout. They're evenly mixed. All of these are homogeneous materials. And then we have to think about what's in here. Water, only one type of thing here, so this is a substance. Milk has fat and weight. It's been homogenized, so it's mixed in together. This is going to be a mixture. Honey, there's more than one type of thing in honey, so that is also a mixture. And brass are two metals. Brass is generally zinc and copper, so since that's two metals mixed together, but you can't make two metals into a compound, this guy is also a mixture. They don't look like mixtures, so sometimes that can be tricky, but those are all homogeneous materials. I use Kool-Aid a lot for an example for your homogeneous mixture, because you know there's more than two things in Kool-Aid. You have water, you have sugar, you have the Kool-Aid mix. Yeah, when you look at the Kool-Aid itself, it looks evenly mixed. This looks all the same. But hopefully when you take a drink off of the top of the glass, it tastes the same as when you take a drink off of the bottom of the glass. So this is evenly mixed, which makes it homogeneous, and that makes it a solution. And because the majority of that solution is water, Kool-Aid is an aqueous solution. Elements and compounds, we don't see too many elements in their pure form when we are just walking around. This is sodium. It's really cool stuff. They don't let me keep it here. See them cutting it with a knife. Sodium, one capital letter element. Sodium chloride, on the other hand, over here, two capital letters. That's sodium and chlorine chemically combined into a different substance, way different properties. Sodium, metal, highly reactive, burns in water. Sodium chloride, white crystals, salt. We put it on lots and lots of our food. We use it to preserve stuff. So make sure you know some examples. Sodium chloride they use a lot. Salt water they use a lot. Some other dichotomous key kind of ways of breaking up matter. So the chart that's in your notes isn't the only way that you're going to see matter broken up. Sometimes they will split it up differently in different sources. So this one is splitting matter into either pure substances or mixtures right away. They're not really using the term homogeneous for the substances over here. They're not using them as adjectives for only one type of thing. They're only using homogeneous and heterogeneous if it's a mixture. So two or more things, only one type of thing, and that's how they've split this category. If there's two or more types of things, they're splitting this into, is it evenly mixed or is it unevenly mixed? Evenly mixed, homogeneous mixture, also called a solution. Heterogeneous mixture, unevenly mixed. Okay. Notice they're using little models. The state is going to want you to be able to use all of these little models to represent different compounds and substances, they're not really expecting you to know what the compound is by looking at them and knowing the different colors. They just want you to use random symbols to model what these things are. It shows a little bit higher understanding of learning if you can abstractly represent the stuff. Over here in pure substances, they're looking at the number of types of atoms. So one type, notice there's only one purplish blue colored atom in here. One type, it's an element. Two types of atoms, but two or more types of atoms, and they are stuck together. That's my high-tech way of saying chemically combined. Notice that they're not separate. Over here, there's two types, but they're in separate pieces. Over here, they are stuck together, so this becomes just one unit, even though it's made of two different things. That's how you're going to identify a compound by looking at pictures. I found this one that shows other models for how they're splitting apart the matter. Does it have uniform properties? So uniform properties is another way of saying the same throughout. No, it doesn't have uniform properties. It must be heterogeneous. So here they have two little sections. If you were to split this into quarters and you count the number of each pieces, this one only has one little tiny red piece over here. This one has mostly red and just a few gray. This one down here only has two gray pieces in it. So in this one, maybe a little bit of that red. So if you take different samples, they're different throughout, heterogeneous. Now they're saying, does it have a fixed composition? What they're saying by fixed composition is the same chemical formula. So water has a fixed composition. It is always H2O. Salt water, on the other hand, sometimes I can use a little bit of salt, sometimes I can use a lot. When we make Kool-Aid at our house, I use less than a cup of sugar. My husband uses like a cup and a half. So our Kool-Aid has a different composition depending on who made it. So if it does have a fixed composition, you move to the next category. If it doesn't, it's a solution. A solution's concentration would be the right word to use here. The concentration can vary. So sometimes you can make, your hot cocoa and you get a lot of substance to dissolve in there. It's really rich and thick chocolatey. Sometimes, you're at the bottom of that big serving can and there's not much left, but you drink it anyways and it's kind of weak, but there's still some chocolate in there. It has a different concentration. If it is the same throughout, if it has the same composition all of the time, then we ask, is it chemically decomposable? That means, can I break it apart chemically? If the answer is no, I can't break it apart chemically, it's an element. Remember we said one type of atom. So again, notice that these atoms are made of two pieces, but they're two of the same kind of pieces. That's still considered one type of atom. That's still an element. If you can break it apart chemically, then it's a compound. And that was two or more types of atoms. And if you look at this model, these little guys are made of one red and two white, so definitely a compound, but all of them are the same. One last thing to cover in our lecture notes. So way down here at the bottom, physical changes versus chemical changes and how we use those to separate mixtures. So remember, a physical change, it's going to change how it looks, maybe, but it's going to be the same substance. It's going to have the same formula. My favorite example of physical changes where it has the same formula, because you guys understand this about water. Solid water. In English, we typically call it ice and not solid water, but it's going to have the formula H2O. And to show you that it's solid, we'll put an S after it. That's how chemists write ice, H2O solid. Liquid water, which sounds really weird because in English we don't refer to it as liquid water. If we talk about water, we're referring to its liquid state. And in chemistry, that's going to be H2O liquid. Ice and water look very different. They still have the same chemical formula. Gaseous water, we typically in English call it steam or vapor. We talk about the water vapor in the air a lot. And when you write its formula, it's H2O with a G for the gas phase. So again, it's the same stuff. Solid water, liquid water, gaseous water, same stuff. Those are physical changes. Check out up here when we write salt water, it's still NaCl. So we have NaCl solid plus H2O liquid. And when we put them together, we get NaCl aqueous. So the sodium chloride still here, and the water is right here, because when you see aqueous, you're going to think dissolved in water. So it's the same stuff. It hasn't changed at all. It has the same formula. It's just dissolved now. So solubility, physical change. Okay, those are the big ones. Ripping, shredding, tearing, grinding stuff up, those are all physical changes. In chemical changes, you're going to get a new compound altogether. So in chemical changes, we're doing some kind of chemical reaction. You know, when you put hydrogen together with oxygen and you make water, then it's different. So you have hydrogen, you have oxygen, you make water. This formula is different. I went from an element and an element into a compound. That's a chemical change. So if you do something that makes a new substance, when it's done, it's a chemical change. Reacts, neutralizes, anything that sounds like burning, combustion, oxidize, burn, those are all going to be chemical changes. Look for those keywords when you're doing those things. Separating mixtures, if it's a mixture, it's going to be done by physical means. The only way you can separate things chemically, those would be compounds. So generally, if it's a mixture, we're going to separate it by physical means. So some of the ones that the state expects you to know, and this is why we did them in lab, they expect you to know that filtering will remove something that is insoluble. So we, add water and the insoluble thing gets caught on the filter paper. Distillation is for separating two liquids that have different boiling points. So you boil one, the one with the lower boiling point boils first. You can recondense it if you capture that steam, and you'll have your two liquids separate. Evaporation, that's one of the easiest ways to get salt out of salt water. So if you want to make salt, you can just grab some salt water and set it out in the sun and wait until the water evaporates out. That's how a lot of countries get their salt. That's how some companies will sell sea salt now instead of just sodium chloride. Instead of mining it out of the ground, you can just get some natural ocean seawater and let the water evaporate. Magnets, remember that the only three metals that are magnetic are iron, nickel, and cobalt. All of the other metals are not. So if you have iron, nickel, and cobalt, you can separate them with a magnet. Sorting, hand sorting through things, that's a great way to sort M&Ms. I know I always used to save the red or blue ones for last, so I'd eat all of the brown ones first to kind of sort through. Sifting, we use the soil sieves, get the rocks and the dirt separated by size. You did that in earth science because you rate different sized particles as different types of rocks and soil, and their size was important, so you put it through those sieves to separate them. That's a physical way of separating things. So those are the big ones that the state wants you to know. We'll practice some questions that ask about how you sort things out, and that wraps up Lecture B.